Slideshow. Where is slideshow? Dobra. No i co było?
Sure.
Tak,
Tak.
Gotowe już? Dobra, okej.
Nie ma kamery.
Tak, Okej, dobra, to zostajemy z tym. Albo bez kamery. Dobra? Zaczynamy swoje działanie.
Teraz zobaczyć.
Dobra,
Problem istnieje. So good afternoon, everyone. With small delay, we are welcoming our today guests, Natalia Rektsini. Natalia is originally from Greece. She did her PhD in Tasmania at the University of Tasmania, and now she's a postdoc in Paris. And she's gonna tell us about the microlensing observation with high angular resolution techniques. So the floor is yours.
Thank you. Thank you. Hello, everybody. I hope, can you hear me? Good. Well, thank you for inviting me and for having me and for coming over here to listen to me talking about the work that I have been doing the last 4 years of my life, and also helped by a group of people that I work with in microlensing. And yes, as Milena said, I'm going to discuss about microlensing and the high angular resolution techniques. Before I start, I wanted to show this beautiful photo that I took in Tasmania. This is where I did my PhD. Not exactly there, but you get the gist. And this is actually Cradle Mountain. And I really like it because in my very messed up eyes, this really looks like, to normal people, probably like a cradle. To me, and maybe other microlenses, like a caustic crossing. So I found that it was very, I don't know, nice to show this to you. Can I make? Yes, good. So I'm going to start with discussing a little bit about exoplanets and the different detection methods and what we can see from each detection method, starting with radial velocities, which is the detection, the method that has given us the first historical exoplanet detection. In this method, we usually it's more efficient with exoplanets that are more massive in larger, brighter orbit separation for the host mass, for the host star, sorry. But of course, now with more high angular resolution spectroscopy, we're able to also detect smaller mass exoplanets closer to the host star, which is pretty amazing. Then we have the transit, which is the method that has given us the larger amount of exoplanet detections. And of course, this technique is more efficient with planetary systems that are surrounded, that orbiting a very bright stars, because this way we can really see the transit phenomenon. And then we have the direct imaging, which is the most direct method you can get, because you literally take a photo of the exoplanet, which I still find very amazing. And of course, this technique is more efficient with very large, massive exoplanets, so ultra Jupiters that are in very wide orbits from the host star, in order to actually be able to observe them and take a photo of them. And then we have gravitational microlensing, a technique that a master student once told me that it's the most out-of-the-box way to detect exoplanets. And basically, we don't really observe the planet or the host star. We really observe how the mass of the planet interacts with the space-time around it. And this way, we will see a curvature. Because of this curvature, the light emitted by a background source star will change its trajectory. And as a result, the mass of the lens, the star and the host planet, will act as a lens, curvating the space-time around it. Unfortunately, there are not a lot of exoplanet detections with this technique, because it's most difficult to detect exoplanets this way. You can't really know when a chance alignment between two stars will happen, and you'll be able to observe it. Also, it's like a transit phenomenon, but it's a once in a lifetime. So if you missed it, you lost it. But why do we bother trying it? Because as you can see here, first of all, with gravitational microlensing, it's the only technique that allows us to detect massive and low mass exoplanets close or beyond the snow line, which is basically where we expect to have the planet formation in the beginning, when the planet is born. And this is very crucial information about planet formation theories. Furthermore, as you can see here, in general, without the techniques, with mostly transits and radial velocities, we can see that more massive stars will have more massive planets. And you don't really expect to have massive planets around low mass stars. And this is not really what we observe with microlensing, not with direct imaging. And the problem is that we don't have a lot of dots. And also we don't have always good precision. So we cannot really know if this is actually new evidence of, okay, your theory is not correct, or if it's just an exception to the law. For this reason, we need more purple points. So we need more observations, which means that, your colleagues that do microlensing, they actually serve a really important cause. They're not just privileged people who get free trips to Chile. Tough crowd. Other people who have laughed at it. So, of course, you have to observe this with telescopes and not with your eyes. If you see rings in the sky, it's not a microlensing event, you need to go home. So we have Ogle, of course, you know it, and then MOA, which these are the historically the first microlensing photometric surveys scanning the skies. Then the last decade or so, we also have Internet, which is the Korean microlensing network. The last year, we also have PRIME, which is the first infrared microlensing survey that started operating in South Africa. And then we also have some small observatories that will do follow-ups once there's an alert, like ours in the Greenhill Observatory at UTAS. So we have been very privileged to have our own two telescopes, a 50 centimeter and the 1.3 meter. We also have a brand new infrared camera. We'll have the camera for a year now, but we haven't really used it because the 1.3 meter mirror is actually in New Zealand, being fixed by the Kiwis. And by the Kiwis, I mean the New Zealand people, not the bird. will be weird to ask the bird to fix a mirror, but hopefully we'll be up and running with her infrared camera by the end of the year. Exciting. And, you know, there is hopefully an event and there is an alert, and it's actually, you know, you can see not just a light curve, but also an anomaly, and this anomaly will be hopefully a planetary system. And I want to say that these are nice light curves. They're not always so full and so clear. But I want to stress out how important it is to have high cadence, to have frequent and constant observations, because as you can see, the planetary anomaly can last from a few days to a few hours. So if you've missed, if you couldn't observe at that moment, then you kind of missed your planet, and then it's much more difficult to do the light curve modeling. It's already kind of difficult, but yeah, your life is much, much worse. And what you will usually, hopefully, observe and get from the light curve will be the Einstein radius crossing time, so the length of the event, the impact parameter. Okay, interesting. Sorry?
It's not PowerPoint. I live in office. I have no PowerPoint.
Oh, great. Okay, you will not see the parallax, but imagine a Greek T over there. So, like the microlens parallax, you cannot always observe it. So this is the case. And then occasionally we can also see finite source effects, like the source radius crossing time and the source angular radius. You're also not, okay, this is that it doesn't like Greek letters. This is very racist of you. But anyway, so occasionally we can see finite source effects or not. This is not the day. And finally, of course, we really want to have the source magnitude and the source color. You're going to see later on that it is quite important. And what we will hopefully get from this is the planet-star mass ratio and the planet-star separation in angular Einstein radius units that you don't see there. And so you see, we still don't really get the actual planet mass or the star mass, which is what we want, because people in exoplanets, this is what they really use. And when you just give them mass ratios, they're like, okay, this is cool, but you know, I don't really care. So I'll go back, write another TRAPPIST-1 paper and invent more jokes about flat lines because I use James Webb time. And all I discover is that that Jupiter morning was cloudy. And so what we usually do is use Bayesian analysis with galactic models, choose the galactic model wisely because results may change dramatically, but still we don't get a real precision. There are techniques to obtain mass and distance high precision. The first would be to actually observe the microlensing parallax. This can happen either if we have observations from the ground and from the sky, so with a space telescope, or if the event lasts too long. Unfortunately, there are very few exoplanet events that can last long enough to actually observe the microlensing parallax from the Earth. And we have seen that you need like good space instruments, like with good appropriate signal to noise ratio to actually be able to use effectively the microlensing parallax. Otherwise, you can get more troubles. Then another way is to actually observe the finite source effect. If you do this, then we can derive the angular Einstein radius. And when we do this, of course, if you know the size of the lens has occurring because of the mass. So basically you get information about the mass. But again, you don't always have finite source effects. And also sometimes it might not be finite source effect, but blending. It's very complicated sometimes to actually know what you observe just from the light curve. And finally, of course, we have interferometric microlensing, which is very new because interferometry is very new. And if you have that, you are a king. or a queen. And basically you can really see the projected images of the source. And I think that this is a really good technique. If you ask people for gravity to, observe a potential black hole, they'll be happy. If you ask them to observe 10 M dwarfs surrounded by super Jupiters, probably not their cup of tea. So maybe, either invent your own interferometer or find other ways. Also, these ways are very nice to observe if you want to have immediate results. But sometimes you want to wait. Sometimes, in Greece, we say good thing takes time. So sometimes if you want to have spare time to go sit in the sunshine, wait a couple of years, do more observations, you want to have more and more observations. So, you really feel that you've earned the result. You really want to have time and work to do. So basically, if you want to do microlensing like a Greek, and then derive a very dramatic, precise measurement, then high angular resolution follow is for you. So far, we have been using Keck, which is a ground-based large telescope that uses adaptive optic techniques in order to do high angular resolution observations, and also the Hubble Space Telescope, which is obviously up in the skies. We don't get to go there, which is sad. And why you want to have high angular resolution images? Because basically, instead of having 5 stars in 1 pixel, you have 5 pixels for 1 star. And this changes your whole life. You will discover the sky. And why do we want to wait and not just go straight ahead? Well, you can go straight ahead, but also you really want to wait. It's because if you, for example, the Susan lens, they have a relative proper motion of 5 milliard seconds per year. If you wait 10 years, then you'll have a Susan lens that they're separated by 50 milliard seconds, which is kind of the resolution of the Keck images, 50 to 60 milliard seconds. And then you can enjoy a really resolved Susan lens, which will give you the separation and the flux ratio and the flux of the lens and the source. And why do you want this? Because having a very precise separation between sensor lens, it can give you the very precise relative proper motion, which then it will obviously give you, if you know the time of the length of the event, it will give you a really, really precise measurement of the angular Einstein radius. So there you have one constraint for your mass and distance. And then also with the relative proper motion, we can really see if our light curve model was correct or not. For example, if we have observed finite source effects, does the light curve model predict a similar relative proper motion, or are we completely out? So then we can go back to light curve and redo the modeling, or maybe solve degeneracies. Finally, the relative proper motion is also is related to the microlensing parallax. So if we use these results while refitting the light curve model, we can also constrain the microlens parallax. So then you have a second mass and distance relation. And finally, if we use the lens, the actual flux of the lens, then we can derive a third mass and distance empirical relation in order to constrain the mass and distance. And finally, if you combine all these 3 relations, as you can see, you can occasionally enjoy a very, very precise measurement. Now, this was a very gentle, nice event. Didn't have a lot of contamination or, I don't know, problems around it. So we did have a very, very precise mass and distance measurement. Unfortunately, it's not always the case. So for example, I have worked on another event where, as you can see, the flux of the lens is really constraining the mass, but we really fail with the distance to the lens. Why is this? This is not caused from the Keck images. Our observations were perfect. We really derived a very, very good separation and flux. This is because of the source. Because actually, in this event, I've been really struggling to define the nature of the source star. And this is because the VI color seems to be strangely blue. And what this means, it means that basically it doesn't look like a star that will be inside the galactic bulge, but farther away in larger distances in the galactic disk, which is, I believe that this is the first microlensing exoplanet event that follow-up observation seems to confirm that actually the source might be farther away. So I have tried different galactic models, and I also used PyLimas, which is using a Gaussian mixture approach with stellar isochrones to try to constrain the nature of the source. And so far, it looks like the source has to be farther away, but still I couldn't constrain the distance. And this is why I cannot constrain the distance to the lens. So this shows that it's not, actually being able to correctly define the distance to the source is also important. And also it shows that we need more and more observations and in different wavebands. So in my opinion, I don't know if anybody has any suggestions, but in my opinion, the only way to really resolve this system would be to obtain high angle resolution images in different bands and really constrain the distance, the nature and the distance of the source. Apart from these works, well, my group and I have worked on different other interesting events. I'm not gonna be like David Bennett and show all of them. They're very interesting. They're on archive. You can go and enjoy reading them. But all this to say that in the last 10 years or so, there have been maybe 20 follow-up papers, and there are a few more to come. And it's very exciting. But as I said, we have like 230 observations of exoplanet detections, 20 to 30 of them, they're very precise with follow-up. It's still not enough to make a really good statistical sample for the exoplanet community. We need more. And we will gonna have hopefully more light curves soon with the launching of the Nancy Grace Roman Space Telescope. I think a lot of you have heard a lot about this. Hopefully, if once it is launched and the survey starts, we expect thousands of new exoplanets. Of course, it will go to lower mass limits because it will be able to detect fainter events that we're not able to do from the ground. And it will also observe about 100 or maybe more free-floating planets with hopefully very low Jupiter masses, but still, and well, you know, hold on. And Roman will be able to conduct follow-up observations of all the microlensing events that it has observed, but it won't be able to follow them all. So it has been shown that another way to increase the amount of exoplanet events that we can enjoy with precise mass and distance measurements is to use Euclid. So I have been showing this slide with all these works over and over the past year, but this is because this has been a work of many people that they have been doing this for much longer than I have. And they have been studying different cases of how Euclid could actually really help collaborate with Roman in order to provide us very precise measurements. And these are a few published work, and there has been a lot of unpublished work, and all these to finally successfully have the Euclid images, the survey conducted in March 2025. Now I know that a lot of you have been asking a lot of questions about Euclid and they want information. Unfortunately, I'm not allowed to share a lot or anything, to be honest. And that is not because we don't want to. I would have loved to be able to show you all the beautiful images that Euclid took, but unfortunately ESA is in charge on this, and these are ESA data, and they're not allowing us to share anything with people outside. Normally, shouldn't be having them either, but well, the Euclid people, they are actually at the Institute of Astrophysics in Paris, and they're really nice, so they're sharing information with us. What I can say is that the observations were successful. I have watched some snapshots and I have watched the mosaic, and well, in my not that experience, but still kind of experience eyes, it looks good. The fields are quite crowded for Euclid people who, you know, they're not supposed to observe towards the galactic bulge. So it actually, once they tried to pass it through the Euclid pipeline, it broke the code. It didn't get us Eurovision though. But they have been working, like all the Euclid people, they have been working really hard on this, which is really nice of them because this is not their purpose. They're not paid for this, and they're doing this because they want to, I don't know, have fun with microlensers. And so I just want to say that, yes, we will hopefully have the images ready to go to actually start using them this month, maybe next month. And then once we have the go from ESA, we will be able to share more information with people outside. So for now, we have 9 frames with a total 29 hours observation time with Euclid. Our plan is to analyze all the historical events, so events that have already been observed with ground-based observations. And this means exoplanets, free-floating planets, black hole candidates, binaries, everything. And we plan to start with all the events that are also in the HST observations that they're actually happening. And this will give us, you know, make a more impact. So hopefully, if we do this, then we will convince ESA to include people outside of the working group. So like a lot of Google people, they're not inside the working group. So this way you will be able to also use the Euclid data, that observations that I know that you really want. So one of the events that is our priority, and my priority, is Google 2013-0341, which, as you can see, have a Keck image epoch from 2013, where obviously source and lens they're aligned. From 2020, where we start to see a resolution, like a small lens appearing. We also have a HST epoch from 2025, where we can see clear lens appearing. And we also have a Euclid, which I can show you. But don't feel bad, I also haven't seen it. I just know that it's there. And this will be, I think, a really interesting event to work on and to publish, both for microlensers and not. So hopefully after this, all of us will enjoy Euclid data before they become public, and you know, everyone can use them. And we don't want that. Well, we want that, but you know, we also want to be the first to have papers. But it's not all sunshine, because well, the pixel scale of Keck is, we have 10 milliards seconds per pixel. With HST, we have 40 milliards seconds per pixel. With Euclid, we have 100 milliards seconds per pixel. And if we, for example, do a fast calculation using the simulated events of Roman that Matthew Penny did for the Baslet 2022 paper, and we adjust the epochs because, as you understand, the Euclid epoch, the Euclid observations arrived much later than predicted, then we can see that pretty much all the Roman events will be inside 1 pixel, which is not great because so far we haven't been able to actually work on observations that source and lens, they're pretty much blended. So this means that we need new tools. Also, we're not really used to, well, it took us 10 years for 20 events. So, you know, we need new tools to actually be able to go faster and actually derive precise mass and distance measurements. And this means that we want tools that they're not going to really focus on the PSF, because the PSF with Euclid and Roman, it's pretty much determined. There are groups that have been working on these pipelines their whole lives. There are people that breathe and live for PSF modeling, for Euclid and Roman. We don't have to do this. What we really need to focus on is how to fit the source and lens separation, flux, and orientation inside one pixel. So I have been working on a code that I called Efsta, after my beloved grandma. And this is a code that is using a method that was came up by Christophe Allard, and it has already been used in a couple of follow-up papers. So this was a script written by Christophe Allard for Christophe Allard, and I can say that I am maybe the only person that had the privilege to have access to this script and finally understand it. So this is pretty much the method that he used, which is not that complicated actually, and everything, we calculate everything from the photocenter of the two stars, and then we fit the total flux, the total flux ratio, the separation between the two stars, and their orientation. And I also added the sky background as a fitting parameter. I'm not going to go into too much details about my code and what I have done, because it's not the purpose. There will be a paper coming out the next month, hopefully. And you will all enjoy it, I don't know, at the beach, if reading this stuff is your cup of tea for the summer. But I'm just going to show some preliminary results for Euclid and Roman of the code that I did using the PSF models of the Euclid and Roman simulations from Matthew Penny. So the results here that I show, they're for the 1 pixel scale, so not for the whole. I did it for up to 3 pixel separation, but we don't really care. But well, we care, but most of the events are inside 1 pixel, so the results that I show are really for 1 pixel. And as you can see, I was really searching for the events where we can have really precise, down to 10% separation and total flux ratio, because this is the information that we need in order to then derive the mass and distance. And this is for Euclid, and this is for Roman. Of course, these are just simulations and not the real data. Hopefully, I'll have the real data next month, and then I'll be able to enjoy playing with them, or try, I don't know. And this is basically, again, for the 1 pixel scale, for the 1 pixel separation, the results where we have both 10% precision for the total flux ratio and the separation for Euclid and Roman, which Jean-Philippe told me not to say this, but it actually looks much better than I expected. And we can definitely do much better. So to conclude, I have no idea how long this took, but I just want to say that the future is now. I am very young in the field, so you know I have been waiting only 3 years, but I know that there are other people young as well, but longer in the field that have been waiting for this moment. But actually, future is now. We have Euclid observations, we have HT observations, and we have a lot of work to do until Roman launching. So we have actually, like, the moment where a lot of people have been waiting for has arrived. We have 200 events to work on. Well, maybe not 200, but you know. And we have new tools that will help us go faster and reach new precisions. So the future of mankind, with all respect, sounds fact, but future of microlensing and exoplanet field looks very bright. And this is what I would call work-life balance.
Thank you. Thank you. Any comments, questions, concerns? Correct.
Okay, so you said that you did simulations under assumption that you know that PSF.
Yeah.
Do you know how accurately you can measure the PSF of Euclid? How well known is it actually?
Well, I think it will depend who you ask. So if you ask Jean-Philippe, he will tell you we will know it 100%. If you ask me, I will tell you, my code will tell me. So for now, I use the simulations that I did. Okay, I expect that I know perfectly the PSF model because I wanted to really see how efficient is the method. But in my opinion, it will be case by case. I think that it will, for Euclid at least, I don't know for Roman because I haven't worked with Roman people. For Euclid, I think that it will be pretty good because there are really people that have been working on this, and I will be working on them in Paris. So if I have a problem, I really have the people there and we can solve it. So I'm quite confident. But you know, there are always cases where things will be bad. But I make the way that I think that I am making the code is to actually take into account how well we know the PSF or not.
So do you expect that depending on the color of the star?
The color? I'm not sure. Sorry.
Okay, and another question I had. Okay, so you cannot tell us about the data, but did you make any estimates how many past planetary events are there in the Euclid field? How many 240 events are there?
We are doing this now.
You know what is the overlap of the first Euclid's epoch, those nine images taken with the finalized Roman fields?
It's pretty much all.
Pretty much. Is it larger?
Yes. Yes.
So I'm happy for people who will be discovering microlensing events in 10 years or 20 years because they will have this.
Yes,
epoch.
exactly.
Although they wouldn't have to go to Keck to observe, so this is a downside as well.
We need to find a new reason
Yes.
to go to hub. I know, I'm working on this.
Any more questions? I'm looking at the Zoom, so. Well, if there is no questions, let's thank Natalia. And we're going for dinner, so if anyone wants to join, just let us know. And next week, there is a guest from Japan who's going to tell us about supernovae, and that's going to be the last seminar of the semester. Thank you very much. Marius was self-sharing and stuff, so but that's why we think we're yeah, and it's like because it's a working group actually on microlensing.